Thank you, everyone. May the divine grace of Goddess Saraswati inspire us to pursue knowledge with humility and utilize it for the upliftment of society. With her blessings, let us embark on today's journey. It is a pleasure for the Department of Electrical Engineering to welcome our chief guest today. In line with DTU's commitment to sustainability, we are honoring our guest with a green token, a sapling that signifies growth, learning, and responsibility towards our environment. So I request the Honorable Vice Chancellor DTU, Professor Prateek Sharma, to kindly present the sapling to our esteemed expert, Professor Ambrish Chandra, as a mark of respect and gratitude. Thank you, sir. The beauty of learning lies in its permanence, so no one can take it away from us. This GIAN course is not only about enhancing knowledge, but also about fostering exploration and innovation in the field of power quality and renewable energy integration. It offers a valuable platform for students and researchers to engage with leading experts, gain deeper insights into advanced controller design and mitigation techniques, and understand how cutting-edge research in power quality transforms into practical, real-world solutions within modern distribution systems. Now, to formally set the tone of today's inaugural session, I would like to invite the person who has continuously encouraged academic excellence, collaborative learning, and international knowledge exchange in our department. I request Professor Rachna Garg, Head Department of Electrical Engineering, DTU, and also the local coordinator of this GIAN course, to kindly deliver the welcome address. Thank you.
A very good morning to all of you. Dignitaries on the dais, Honorable Vice Chancellor, DTU, and Chief Guest of the program, Professor Prateek Sharma, International Faculty, Professor Ambrish Chandra from Montreal, Canada, Coordinator of this course and Director, IIIT Bhagalpur, Professor Madhusudan Singh, Associate Head of Electrical Department, Professor Mini Srijay, Coordinator of course, Dr. Ankita Matta, other dignitaries present, Registrar, Mr. Binod Dole, Controller of Finance, Mr. G.C. Prasad, Director, Narela Campus, Professor Narendra Kumar, my esteemed colleagues, faculty members, participants, students, ladies and gentlemen. It is my proud privilege to welcome you all to the inaugural ceremony of this important 5-day GIAN course on recent advancements in power quality based controllers with grid integration of renewable energy sources, design, mitigation techniques and their performance analysis at the distribution level, scheduled from December 1st to 5th, 2025. This course is not only academically relevant, but is also of national significance. The engineering challenges of today are deeply interconnected. Whether it is sustainable buildings, resilient infrastructure, or smart energy systems, our disciplines are increasingly converging. Renewable energy integration is an excellent example of this convergence. And in this regard, I would say this is a very timely and relevant course that we are organizing in DTU. Here, I would like to inform that this is the 10th GIAN course that our department is organizing. In phase 4, total 4 proposals were submitted from the university and 3 gets approved. 1 was by biotech department and 2 were from electrical. One we had already organized in March. It was on reliability systems, and the resource person was Professor Lalit Goyal. And this is the second course of phase 4. Also, I am happy to inform that in phase 5, total record number of 19 proposals were submitted from the DTU. These proposals are under various stages of scrutiny, and it will take around 4 to 5 months for the process to complete. Organizing such programs are not possible without the help and support of our Vice Chancellor, sir. I would like to welcome our Honorable Vice Chancellor to this inaugural ceremony. Sir is always there to encourage and motivate us in all our endeavors. Thank you, sir. Today also, despite his heavily booked schedule, he has accepted our invitation to grace the program. Sir, we are really thankful to you and welcome you to our department and to this program. We also like to welcome Professor Amrish Chandra, international faculty for this GIAN course. He is a very well-known figure in the area of power quality, renewable energy, etc. Sir, welcome to DTU and Electrical Engineering Department. I welcome all the dignitaries present here and esteemed faculty members of Electrical Department and from other departments who are present here in the inaugural function. Your presence will motivate the participants further. Last but not the least, we would like to welcome all the participants, especially who are from outside DTU, to our university and to our department. I urge them to go through the labs of electrical department, as we really have state-of-art labs in the department, and you will definitely be benefited by seeing our labs. Also, I would like to congratulate the organizers for curating this timely and meaningful program. I am confident that over the next days, the discussions, hand-on sessions, and knowledge exchange will inspire new ideas and empower all the participants. I wish the course a great success and look forward to seeing impactful outcomes of the research, innovation, and industry collaboration. Once again, thank you all and welcome to the GIAN course.
Thank you so much, ma'am. Now, to give us a brief introduction of this GIAN course, I now invite Professor Madhusudan Singh Sir, Director, IIIT Bhagalpur, and also the course coordinator GIAN. Professor Singh brings over 3 decades of distinguished academic and research experience, having served in multiple leadership roles at GTU and contributing extensively to the field of power electronics, motor drives, renewable energy systems, and electric vehicles. He has supervised numerous PhD scholars, authored over 150 research publications, and has been instrumental in establishing a Center of Excellence for Electric Vehicle and Related Technology, EVRT, at GTU. May I now request Professor Madhusudan Singh Sir to give. Thank you.
So very good morning to all of you. The chief guest of today's function, Honorable Vice Chancellor, DTU, Professor Pratik Sharma Sir, our international faculty, Professor Amrish Chandra Sir, the ETS Montreal, Canada, my own head of department, Professor Rachna Garg, and also the local coordinator of GIAN, my colleague Professor Mini, my other colleagues present here, the co-coordinator of this program, Dr. Ankita, officers of DTU who have joined recently. In fact, I left just a few months back, DTU, and all participants, ladies and gentlemen, it's all a matter of great pleasure, honor for me to be part of this function today. In fact, this course we submitted prior to leaving for Bhagalpur. That was GIAN Phase 4 when proposals were invited and we submitted, and fortunately 2 of those programs are sanctioned. One we conducted a few months back. This is the one which we are going to do. And I am very happy that Professor Rachna told us that in GIAN Phase 5, more than 19 proposals are submitted. So that's again a matter of great pleasure to see. GIAN, I hope you all know, is a scheme of Government of India, Ministry of Education, started long back, 30th November 2015. So it is completing almost 10 years. And over a period of 10 years, you see all over the country, more than 3,000 such courses are organized, where international faculty from almost all parts of the world are invited. And it's a great opportunity for India to learn from our international experts. In fact, one of the objectives of that GIAN scheme is that increase footfall of foreign experts on Indian land and get benefit in terms of academics and collaborations. So obviously the 5 days stay of Professor Amrish Chandra will benefit all of us to make a micro-credential, what our VC Sahab used to always advocate, that every professional must have some micro-credential, and micro-credential is nothing but a small specialization. We have a broad specialization always, but you should have a small specialization like this, where you just study a topic for 10-15 hours and have some specialization, some kind of depth in that. So I think if you all, especially participants, seriously attend these 5 days, you will all have a micro-credential on power quality. And power quality is such an area very close to my heart. In fact, many of my colleagues have worked, fortunately Professor Mukhtiar, who is also the one of PhD student of Professor Amrish Chandra, worked in Montreal. And many of our colleagues have worked in power quality. Today we have more than 7-8 people of electrical engineering who works in power quality. So power quality is such a area which is a very emerging and interesting area. I was just talking to Professor Amrish Chandra that this subject, power quality, though we call power quality means quality of power, it is little misnomer. It is something which is quality of voltage and current. So if the voltage and current quality we maintain, power obviously maintained. Now why we talk about power quality, I will just cite an example. This is, I think, the 16th GIAN course we are conducting in campus of DTU. Earlier we invited almost 15 experts from different corner of world. Fortunately, I was also the local coordinator, so I know them. One of the experts told that, why you talk about power quality? We said that in India the quality of power is not as good. So we don't talk power quality, we usually expect presence of electricity. So if the electricity is available for 24 hours, we say it is a good power quality. But in international sense, when they call power quality, he said that, oh, it is like this. I said, sir, there are still some part of our country who are not able to receive electricity for 24 hours. He said that I belong to UK and I am almost 75-year-old. I have never seen any power cut in my region. So I also surprised that is it possible that one can ensure a power quality or power reliability to such an extent. But I think this is the reason that this topic has become so important, that people started thinking how to ensure the blackout, that there is no blackout and there is a continuous power supply. That is one very elementary requirement. But other requirement is which quality of power is the power which you say that high quality power. I still remember 20 years back, I was just attending one course in IIT Delhi, and there was one professor, C.M. Bhatia, sir, शायद जानते होंगे. So he was starting one power quality issue, and they said that you are all laymen, do not know what is power quality. I will simply say power quality means a very high grade electricity. So I said, high grade means what? Very costly? No, not costly. A power which is not distorted, it's very clean power. मैंने कहा सर पावर क्लीन का तो आजकल लोग दूसरा सेंस समझते हैं. क्लीन पावर मीन्स ए पावर विच इज जनरेटेड नॉट थ्रू कोल एंड ऑल, इट इज कॉल्ड ए क्लीन पावर. He said no, clean power means a power which is pure sinusoidal. So when we talk about power quality, we mean a AC supply which is pure sine, and those who are engineers might be knowing pure sine is a waveform which has no harmonics. If you find the THD of a sine wave, it will be 0. So no distortion. And it is the quality of voltage which we try to maintain pure sine. And for that, whatever the mechanism compensation we want to do, that is done through power electronics. And I think Professor Chandra will talk, all this topic for next 14-13 hours. Starting from what is power quality, what are the standards internationally used, especially IEEE 1547 standard, which has become very relevant nowadays when we are integrating a lot of renewable energy and all. So Sir has planned a very systematically capsule of 14 hours. And my only appeal to all youngsters is don't leave any single capsule of that basket. Because if you learn these 14 hours, I am sure confidently you can say I have a micro credential in power quality. And I think that is our main objective to organize this function. Professor Chandra is a very senior faculty. He is a professor of Montreal, ETS Montreal, Canada. Fortunately, the Madam Chandra is also a graduate of this place and also a faculty in Concordia University. Concordia University is also a very well-known university. हमारी इलेक्ट्रिकल में कुछ मशीनें हैं जो वहीं से बनी, तो इसलिए हम लोग जानते थे. तो फॉर्चुनेटली सी इज ऑल्सो इन दिल्ली, एंड मैं तो सर से रिक्वेस्ट कर रहा था कि एक सेशन में मैम को भी हम बुलाएंगे, so that you get some exposure on that. And sir is an adjunct professor in many of the university in China and other part of the world. So I am really grateful to Professor Chandra sir for sparing his valuable time being with us for 5 days. I visited once to Professor Chandra lab in Canada in 2012, and I was really impressed the kind of culture, the kind of research eco-environment he has developed there. So since then, 2012, I was trying to how to bring Professor Chandra to DTU, and fortunately we got that opportunity and he is here. So thank you all, and I am really grateful to my Vice Chancellor sir, Professor Pratik Sharma-ji, a thorough gentleman, and in fact for last GIAN proposals, he was encouraging me that we should upload as many proposals as. In the meanwhile, I have to shift to Bhagalpur, so that entire thing I handed over to Professor Rachna, and Rachna is doing very well. In fact, for just 2 months, he has submitted almost 19 proposals, and I am 100% sure out of 19, at least 10 we will get. And that way, at least 10 more foreign experts will be here to teach all of us some topics. So with this, I have a lot of things to share with you, in fact, because DTU always in my heart, very close to my core heart, and I always learn from DTU. I always believe that what I am today is because of DTU. So thank you all for joining this program, and once more my appeal is that don't leave any lecture of Professor Chandra. I will also try to attend as many. So thank you all, and thank you for joining this function.
Thank you, sir, for such an inspiring words, and we all are very eager to attend this course now. So it is my privilege to introduce our distinguished expert for this GIAN course. Professor Amrish Chandra is a renowned professor of electrical engineering at École de Technologie Supérieure, ETS Montreal, Canada, a premium institute in power engineering education and research. He brings with him decades of rich international academic experience, having completed his BE from University of Roorkee, MTech from IIT Delhi, and PhD from the University of Calgary. Professor Chandra's primary research focus on power quality improvement in distribution systems and integration of renewable energy sources via advanced power electronic converters, topics that align exactly with the theme of our GIAN course. He has authored hundreds of research articles and book chapters, and also co-authored the well-known book, Power Quality, Problem and Mitigation Techniques. Over the years, his pioneering work has gained global recognition, as seen in a citation record that spans thousands of references and a strong H index, underlining his impact in the academic community. He has also delivered as distinguished lecturer for major international societies like IEEE Power and Energy Society and IEEE Industry Application Society, and has delivered keynote lectures in over 30 countries, disseminating advanced knowledge on power quality and renewable integration. He is a recipient of many prestigious awards, with recent are Gold Medal in IEEE Montreal Section, Bimal Bose Award, IETE India, Distinguished Alumnus Award, IEEE Roorkee, and the list goes on. We are truly privileged to have him as an expert on this GIAN course. His insights and experience will tremendously enrich our understanding of modern distribution level challenges and mitigation techniques. I now invite Professor Amrish Chandra to address this gathering.
Thank you very much for the introduction. I want to thank DTU, the Honorable Vice Chancellor, Professor Pratik Sharma, Professor Madhusudan Singh, Professor Rachna Garg, Dr. Ankita Matta, and there are so many people, dynamic people working here, like Professor Mukhtar Singh, Professor Alka Singh, and so many people. Professor Mini is there. So I am so happy to come here. I always thought that I should also go and deliver lectures in English. Because for last 34 years, I am teaching in French. Can you believe I am teaching electrical engineering in French? So it is a very good opportunity to meet such dynamic people, the participants, young and dynamic people who are the future of India. So it is a very good opportunity for me to teach from the basics. So this is how we planned our lecture. So we will start very slowly. We will slowly see, okay, what are the basic issues of power quality? What is basically the power quality? This is what Professor Madhusudan Singh was saying. He gave so many insight he has already given. So this is what we will do. Slowly we will go. We will see what is power quality. What are the main issues? Okay, what are the different factors? And what are the standards, IEEE standards, the one which are related to this course. Otherwise, there are thousands of standards, but we will concentrate on power quality. And then slowly we will move to, you will say, why we are discussing 4-year series here? Because we want to know about the harmonics. Why we are discussing symmetrical component, old theory? But I tell you, this is the basics. Symmetrical component theory and its application in unbalanced and distorted system. How the different transformer, 3-phase transformers, will react to different types of harmonics. How they are giving the phase shifting. So these are all classical and being used in the industry. So the young engineers, first step, what is the first step? The first front defense. How not to use the modern equipment, whatever available equipment is there, you should make a full use of that equipment to avoid, to generate harmonics, to cancel the harmonics. So this is a very important step for a young engineer to understand that if you are in the industry, whatever are the resources, you have to manage those resources. 20 years ago, I visited Bombardier company is a very big company in Montreal. They make aeroplanes. They have different labs. So I visited their drives lab, and they were having so many harmonic problems inside the industry, inside that lab. They were not able to manage. So the solution they proposed, okay, we will put the power quality conditioner. So one ABB power quality conditioner was there. So it was costing $10 million, and then $2 million were given by Hydro-Quebec, the utility company. But why that situation arose? This is the important thing. Why the engineers did not pay attention at the very beginning when they were buying the three-phase transformers and those things. So the manager will say, okay, this is the production line. Okay, we have three-phase transformer, we have drives, we have non-linear load. And now we want to put the second line of production. So presently, that line of production is working fine. Whatever harmonics were generated, they were manageable. So the manager will say, okay, what we should do? Immediately, an engineer will say, why don't we buy the same production line, same way? Because it is already working fine. I tell you, this is the worst decision an engineer can take. Because you have to see what harmonics are generated by the first production line. It's fine, they are not giving any problem now. But now you are putting the second line, and then those harmonics will be added and they will create more problems. And this is what happened in that Bombardier lab. So there were so many harmonics, they were adding up, and finally they were not able to work. So they had to use the modern equipment. So we will discuss those things. Then slowly we will go to your active filters, shunt filter, series filter, hybrid filters. And then we will see some standards. And then we will go to renewable energy integration, grid codes related with the renewable energy integration. And then we will move to this, what we call climate problem, climate change. So this is what we will see a little bit in last two lectures. We will go see what happened in COP21 conference. In 2015, there was a conference organized by UNO, and a Paris Agreement was signed in 2015, and they kept 2 degrees centigrade limit. Above pre-industrial 1880, they started having the weather data, so they put, okay, we should not go above 2 degrees centigrade. $100 billion have to be invested every year in renewable energy projects. Then COP26 came, they said, no, 2 degrees centigrade is very high. We should keep 1.5 degrees centigrade. So you see, this is how it is evolving. So we started integrating more and more renewable energy sources. So this is what we are going to discuss, and finally we will see what is happening around the world, and that's it. Thank you very much for giving me this opportunity.
Thank you so much, sir. And I must agree that this 5-day course will help us all to improve our knowledge background in this power quality area. It is now my honor to invite our respected Vice Chancellor, Professor Prateek Sharma, Professor Sharma pursued his PhD in environmental engineering from the Department of Civil Engineering, IIT Delhi. He completed his ME in hydraulics and BE in civil engineering from Delhi College of Engineering and now our very own DTU. He brings with him more than 28 years of rich teaching and research experience. His area of work spans environmental system modeling, statistical applications in environmental and water resources engineering, and environmental risk assessment. He has published extensively in high-impact journals and has authored 2 books in the area of vehicular pollution modeling and stochastic modeling, along with a monograph. Professor Sharma is also deeply associated with national-level environmental initiatives. He is a fellow of the Wessex Institute of Great Britain, a recognition of his outstanding contribution in air quality modeling. He is a member of National Knowledge Network, constituted by the Central Pollution Control Board to support the National Clean Air Program of the Ministry of Environment, Forest and Climate Change. With a brief introduction, may I now very humbly request Professor Prateek Sharma, Honorable Vice Chancellor, Delhi Technological University, to kindly address the gathering.
So good morning all of you. So first of all, on behalf of the entire D2 fraternity, my colleagues, students, I would like to welcome Professor Chandra and would really very grateful from the core of my heart for very kindly agreeing to be part of this GIAN program. And in fact, before I say about others, especially Professor Madhusudan Singh, who is responsible for all the GIAN activities in DTU. And in fact, if we see anything related to GIAN, mostly you will find his stamp there. And in fact, and this was, he started, obviously there were several initiatives that he had taken earlier, and before when he left for Bhagalpur as director, obviously this, as was told, this was that he started. And I believe we got this project because we wanted him to be here to address the audience. This is a good reason for him to be back. And I miss him a lot. So, in fact, for the participants, I would mention, Professor Chandra's, I had heard so much about him, but it's my privilege and pleasure to meet him in person today. And incidentally, I got to know also that he is a batchmate of my PhD supervisor also from Roorkee. And incidentally, these days when we talk about, people say, especially in the for participants especially, I'll mention, if we, these days people talk about, so much information coming in through internet, YouTube, and AI coming, so what will happen to teaching profession? And it is such a comforting experience to see and see how the manner in which Professor Chandra, reached out to the audience. And this is what, the quality of teaching makes the difference. The steady pace with which he basically addressed the audience, which basically, even I am a civil engineer, but I got a feeling that I must attend his class. Because the thing is, the manner in which he approached the entire topic, the patience and the calmness with which he was trying to explain exactly the 5-day, from the very fundamentals to, in fact, he touched climate change and sustainability. And this is something, people talk about these days of green energy, sustainability, sustainable development, and how to attain the sustainable development goals. Usually what happens is, we teach an isolated course in sustainable development or environmental studies and think that our job is done. It is actually, through every course, wherever some connect on climate impact is there, one needs to integrate that, and whatever we do, if we are able to integrate our course in the line of what he touched upon. And because 2 lectures he mentioned would be, and he spoke about COP, he spoke about climate change, he talked about green energy, starting from the very elementary topic with which he started his talk, address, which basically tells, the 360-degree view that he has about his subject and the topic he's going to speak. And I consider all the participants to be fortunate that they are being, taught by somebody as distinguished as Professor Chandra. I mean, I was really impressed, the manner in which he brought up in a very, in 5 minutes, he, जिसको कहते हैं ना हिंदी में गागर में सागर, और पूरा का पूरा he was able to connect starting from the very elementary aspects of power quality, and then touched upon the how it is impacting the various aspects of climate change. These sensitivities are required when we teach, and it is not, we can't actually teach any subject in isolation. We have to integrate each and everything, and without compromising on the fundamentals, because AI, whatever tools these may come, but they can't replace a good quality teacher. Because what happens is that when we were students, our teachers used to tell us that हम slide rule से हम सीखा हमने, हमारे टाइम में कैलकुलेटर आ गए थे, उसके आज के बच्चों थोड़े और आगे बढ़े तो स्मार्ट कैलकुलेटर्स आ गए थे, प्रोग्रामेबल कैलकुलेटर्स आ गए थे. लेकिन आप ये मानेंगे, मतलब so many years in teaching profession, जो आपकी sharpness पहाड़े याद करके आती है, वो आप जो मर्जी कैलकुलेटर करिए आप नहीं आती है. So that is what it makes a difference. So that it is important, especially, and that too when I teach statistics, or people try to एकदम straight away jump on the packages, software packages, without realizing what the package is doing for you. So if your fundamentals are strong, जितना मर्जी बहाव AI का और किसी चीज का आ जाए, आपकी firm जो roots हैं वो आपको हिला नहीं पाएंगे. So obviously we can't actually have an ostrich mentality कि AI आ रहा है, इंटरनेट आ रहा है तो अपनी आप आंखें बंद करके नीचे जाइए. वो आपको करना क्या है, आपको अपने फंडामेंटल्स को और ज्यादा स्ट्रॉन्ग करना है. और दिस इज व्हाट इन फैक्ट आई नोटिस्ड इन प्रोफेसर चंद्रा's initial remarks. एंड इन फैक्ट मैं बार बार जितनी तारीफ करूं डॉक्टर साहब आपकी कम है. और बहुत बढ़िया, बहुत अच्छा लगा. और in this day, this age, we need to have such people around, because this gives a sort of a confidence in doing the right things in a manner in which they ought to be done. And in fact, Professor Madhusudan emphasized upon, about the importance of GIAN courses and having people of international repute in our midst, so that they share their experiences and we get to learn more about, several initiatives or efforts that are being made, not in elementary teaching, but also in terms of research, other activities that are happening. And obviously that exposure we want to give to the various participants and to our teachers, so that whatever we do in the Indian context, we are at the same place where the academic and research activities are taking place. Earlier, there were issues and challenges in terms of usually these lectures were organized because obviously this opportunity was created by Government of India. But now things are changing, as also was highlighted by Professor Rachna and Professor Madhusudan. The expectation is that these should not be just restricted to a mere formality of completing an exercise of getting the funds from the government and inviting somebody and then just completing the task. With the NEP coming in, and obviously with the UGC guidelines of having possibilities of collaborations with the foreign institutions in terms of joint degree, dual degree and twinning degree programs, these opportunities that get created should be helpful in carving out such collaborations with the institutions from which these distinguished faculty members come. And obviously, as again I would mention, Professor Singh mentioned about micro-credentials. I mean, for the participants especially, I would like to mention, please don't consider this to be another course which gets in your CV, okay, that you have attended a course and then obviously for your promotional purposes, it will add, for that reason. Please consider yourself to be fortunate that, you have somebody as distinguished as Professor Chandra, and the manner in which the whole course has been organized, there's a concept of micro-credentials. I won't repeat what Professor Madhusudan Singh mentioned. Micro-credentials are basically the skills that you acquire in a short duration. And obviously we are trying with DTU, we are trying a lot to do, especially in the context of micro-credentials. This happens to be again something similar to what we wanted to have. And incidentally, we are trying to experiment with bringing in more practice, bridging the theory-practice gap, and the department that we have chosen to create that template is electrical engineering department. So in all parameters, in fact, what we have observed is that this is one department which is doing quite well in all the parameters, quite exceptionally well. And incidentally, we are trying to do several other initiatives through this department that will really help in creating a template, not even in terms of micro-credentials that he mentioned, but also bridging the theory-practice gap and having something really special, which would be a template not even for the DTU, but for the country. That is what the whole plan is. And I would just, through this platform, I would just request Professor Chandra to accept our invitation to be a distinguished professor on honorary at DTU, and by his presence, it will only add value to our department and to the institution. And I would like to thank the entire electrical engineering department for conceiving this GIAN course, and I do hope that participants, after 5 days, when they go out of this course, there will be a substantial delta change in their value added to their existing repertoire of knowledge and the experience that will carry with you. And obviously the idea is to disseminate that knowledge to your students. And obviously with such experience hand, it reassures the confidence in basic quality of teaching that is required to be emphasized in as much as possible manner as should it to be done. Thank you so very much.
Thank you so much, sir. We are very much honored to have such esteemed, distinguished members and dignitaries to present among us. As a token of our deep appreciation and respect, I now request Professor Prateek Sharma, Honorable Vice Chancellor, sir, to felicitate our guest of honor, Professor Ambrish Chandra. Would like to request all of the other dignitaries on the dais to join him. Thank you, sir. Now I request Professor Madhusudan Singh, sir, to felicitate our esteemed speaker, Professor Ambrish Chandra, with IIIT Bhagalpur, Angavastra. Thank you, sir. Again, I would request Professor Madhusudan Singh, sir, to felicitate our Honorable Vice Chancellor, sir, Professor Prateek Sharma, with IIIT Bhagalpur, Angavastra. Thank you so much, everyone. This course stands as a treatment to the tireless efforts and unwavering dedication of our coordinators, working team, and devoted volunteers. In recognition of their exceptional contribution, I now invite coordinator of this course, Dr. Ankita Matta, to deliver the vote of thanks.
Good morning, everyone. It's truly a pleasure for me to deliver the vote of thanks on this special occasion when we begin formally our GIAN course on recent advancements in power quality based controllers with grid integration of renewable energy sources, design, mitigation techniques, and their performance analysis at the distribution level. First, I would like to express my heartfelt gratitude to our Honorable Chief Guest, Vice Chancellor Sir Professor Prateek Sharma for taking time from his busy schedule to be with us today. Sir, your vision for DTU always inspire us and motivate us to create impactful academic activities like this one. My sincere thanks to our distinguished international expert, Professor Ambrish Chandra sir, for joining us all the way from ETS Montreal, Canada. Sir, we are truly honored to have you here. Your vast experience in power quality and renewable energy integration brings tremendous value to our students, researchers, and faculty. I would also like to thank our registrar, DTU, for the strong administrative support extended to us throughout the planning of this course. My heartfelt thanks to Professor Madhusudan sir, our GIAN course coordinator and director, IIIT Bhagelpur, for conceptualizing this course and for his academic leadership when shaping its content. My warm appreciation goes to Professor Rachnagar, our local GIAN coordinator and head Department of Electrical Engineering. Ma'am, your guidance and support have been central to making this program possible. My special appreciation and vote of thanks goes to Professor Narendra Kumar too, sir, and Professor M. Rijwan sir. Sir, your support and contribution is exceptional for organizing this course, and we are unable to organize this course without you. I would also like to acknowledge the support of the Associate Head of the EE Department, the Controller of Finance, and all our respected faculty members and staff from Electrical Engineering Department. Each of you have supported with your ideas, thoughts, and collaborative efforts. To all our participants, thank you for joining this course with such enthusiasm. Over the next 5 days, we will have the opportunity to learn directly from our international experts and national experts, gain hands-on experience and exposure to modern power quality controllers and deepen our understanding of renewable energy integration challenges. I am confident that the insights you gain will help you all over academically, but also in future research, industry application, and real-world problem solving. Finally, a very big thank you to administrative, accounts branch, and support staff who have worked tirelessly behind the scenes to make today's inaugural session smooth and successful. With that, I once again thank to everyone present here and wish all the participants a truly enriching and inspiring learning journey ahead. Thank you.
Okay, I now invite all the esteemed guests, faculties and participants to join us for the group photograph. Please come ahead to the dais.
आफ्टरनून हो चुका है, 12 बज चुके हैं। हेलो चेक, हेलो हेलो माइक चेक, हेलो चेक माइक चेक। तेरी यारी लाइव का सिस्टम है ना।
नहीं फिर रिकॉर्डिंग करनी होगी ना सर. Can I start now? Okay, it's fine? Okay, thank you very much for your hospitality, and I see some students are there, so it's a very good opportunity to learn, start. So this first lecture is basically introduction to power quality. Okay, and you can see the outline of the presentation. So first we will see what is the definition of quality of electrical energy, as Professor Madhusudan was explaining, right? Justification of interest in electrical power quality, classification of power quality problems, because there are so many problems related with power quality problem, different factors concerning the harmonics and some standard related to power quality. So this is what we are going to discuss. So if you see what is power quality, so this is what is the question, as Professor Madhusudan was saying. So during the transmission, distribution and utilization of electrical energy, the voltage may vary. Why the voltage will vary? There are so many phenomena why the voltage may vary. Perhaps there is a fault in the line, or there is a very large size induction motor is starting. So as you know, during the starting in the large size induction motor, they may take 5 or 6 times of rated current may flow, so that heavy current will flow through the impedance of the line, and because of that voltage drop is there. So at point of common coupling there may be some voltage sag, or perhaps there is some capacitor bank. Okay, capacitor bank we are switching on or off. So if you are switching off the capacitor bank, what is the purpose of capacitor bank? That it is providing the capacitive reactive capacitive current, so that the source does not have to provide the reactive current to the load. So if you are switching it off, that reactive current will be supplied by the source, and the current will increase, and perhaps it may cause the voltage drop. Or there may be a large load which is switched on or switched off. Because of that, there may be some voltage variation. So this is what the term power quality is associated with, this variation of voltage and electric energy. Sometimes customers say the power quality is the power without over voltage transients, without voltage sag, without short or long-term interruptions, without flicker. So there are so many things. So the power quality is related with those things. According to some customers, power quality is concerned by a perfectly sinusoidal wave, a constant amplitude and a constant frequency, because at certain application, for example, in the hospital, if the frequency changes or voltage changes, perhaps some equipment may malfunction and the life of patients may be in danger. So that's why it is very important to have constant sinusoidal voltage and constant frequency. Or maybe some electronic equipment also. According to utilities, power quality is associated with the reliability and show statistics demonstrating that the system is 99.98% reliable. This is what utilities may say, like you have DESU, I think you have DESU here. I don't know if it is still there, or UP Electricity Board, or those things. So what they will say, okay, in 24 hours, the electricity was not there for few minutes. So if electricity is not there, but here this may be different, but I am talking about North America. Like if electricity is not there for few minutes, so this is right that it is very reliable, 99.98%, because in 24 hours, if few minutes of electricity is not there, you are still reliable, 99.98%. But what impact it will have on industry? So it is just an estimate. Only in North America, every year, more than $100 billion are lost. $100 billion are lost every year because of the short interruptions and those things. So though it may look very small thing, okay, for a few minutes electricity was not there, but it has very high implications. According to the load equipment manufacturers, quality power may be defined as those characteristics of the power supply that enable the equipment to work properly. Okay, but these can be very different for different equipment and different manufacturers. For example, here you have 220 volt. I remember when I was a kid, sometime voltage was 180, 190 volt. Okay, so we used to, for the TV, we used to have a knob, we used to adjust the voltage, right? So for some application like radiators to heat the room, the voltage may vary, okay, 190 volt or 230 volt or so. It is fine, they will still work and proper. But in some equipment, they may fail, they may malfunction if there is a variation of voltage. So it depends basically, different equipment, different manufacturers, what is their standard. Finally, power quality is a customer-driven issue, and the customer's point of view is the most important. Therefore, a power quality problem may be defined the following way: any power problem manifested in voltage, current, or frequency deviations that results in failure or misoperation of customer equipment. So there we say there's power quality problem. Power quality equal to voltage quality, as Professor Madhusudan was saying, this is what generally say, power quality is voltage quality. So the power supply system, utilities can control the quality of voltage. It has no control over the currents that particular load might draw. Okay, so the generators may provide near perfect, because you know we are having large generator, they are providing near perfect sine wave. The distorted currents pass through the impedance of the system can cause the distortion of voltage, because if there is a fault in the line currents, and it may, that current, heavy current is passing through the impedance of the line, and it may cause voltage sag. Like lightning stroke, if there is a thunderstorm and lightning stroke may cause impulsive high voltage which may damage the equipment, like your transformer may be burned down, right? Currents for harmonic producing load. So these non-sinusoidal currents, they are flowing through the impedance of the line, which will cause the voltage drop, distorted voltage drop. And finally, at the PCC, point of common coupling, you may have distorted voltage. So what is PCC? Point of common coupling. Point of repartition of responsibility between the utility and the customer. That is PCC, point of common coupling. it is the responsibility of the utility to provide the voltage and current without any pollution. Although the current is the responsibility of the customer, right? So it is the responsibility of the customer not to distort the voltage and the current. So as you can see, some example of PCC, point of common coupling. So this is the utility system, supply system, and here is one customer, suppose under study, and this is the transformer of the customer, and there are other customers here. So basically you are saying here, this is the point of common coupling. But in this example, you can see this is the utility system and other customers, and this transformer is perhaps provided by the utility company, and so PCC is here basically. Point of common coupling where many customers are connected there. So that if one customer is creating problem, so PCC, it will be reflected on the PCC, and the other customers will also get affected. There was a survey which was done a few years back on the causes of power quality. So this is the perception of the client, and this is the perception of the utility company. So you can see there are some changes in perception. For example, clients say, okay, natural cause is 60%. Okay, what is the natural cause? Like, as I discussed, there is a thunderstorm and lightning stroke, and because of that, transformer burned down. Or there is a storm came, hurricane came, and the tree fell on the distribution line. So those are the natural causes. So according to the perception of the client, 60% causes, while the utility company says it is 66% cause. While the problems caused by utility, according to perception of utility company, it is only 1%. And according to the client, utility has 17% of the problem. Sometimes actually, you know why this perception is different? Because perhaps sometimes the equipment of the client is very old, and if there is some variation in voltage and frequency, so it may malfunction, then the client may blame the utility, okay, because of the bad quality, my equipment did not function. So this is basically a difference in perception, right? And the customer is 12%. You know what happens that suppose there is some large capacitor bank and it is switching on and off, which may generate transients, and because of that your variable speed drive may trip. So customer will say, okay, this is caused by the capacitor bank installed by the utility, but the utility may not see this thing. So that's why difference of perception. Like from customer point of view, it is coming from the utility, while there is no monitoring equipment for that, so that's the problem. Okay. Neighbors, 8%, according to the clients and neighbor. What the neighbors can cause? Sometimes what happens, there is a one client which has the linear load with reactive power, and it has put the capacitor bank at the entry of the industry to improve the power factor. But there is another neighbor, some industry nearby, which is generating harmonics. So those harmonics are attracted by the capacitor bank of the earlier client. And those harmonics will come and they will heat up, and sometimes they may burn the capacitor bank of another client. So this is what happens, problems caused by the neighbors. Justification for interest in power quality: load equipment is more sensitive to power quality variation than equipment used in the past. Why it is more sensitive? Because now we are using more and more electronic equipment, DSPs and those, so they are more sensitive to variation in power quality. Increase in harmonic level on power network. Why there is an increase in harmonic in power network? Because many times utility companies ask the client to improve the efficiency of their equipment. So to improve the efficiency of the equipment, they will be using power electronics, converters and those things, and then it will increase the harmonics. But sometimes utility companies they encourage customers, like I remember 15 years ago, Hydro-Quebec is the utility company in Montreal in Quebec province. At that time, LED bulbs came in the market, and Hydro-Quebec was encouraging everyone to buy those LED bulbs because they will consume less power. Okay, so why Hydro-Quebec was giving 50% off on all those bulbs? Because so that more and more customers buy those LED bulbs and they put, and why? Because it will increase the efficiency, less power consumption, then they don't have to build the new power plants. They may delay the construction of power plants. Otherwise, if they don't do anything, if they don't increase the efficiency, if they don't encourage people like this, then you will need more power plants needed, more transmission line, more right of way, so it costs money. So it is in the interest of the utility company to have the more efficient equipment at client's home so that less power is consumed. Increase awareness of power quality issues by the end users. Now everybody is aware that, okay, my equipment may malfunction if power quality is not good. So they may complain that, okay, utility company has to improve the power quality. Many things are interconnected in the network. Integrated process means that the failure of any component has much more important consequences. The cost of short and long-term interruption runs in billions of dollars, as I have already told you. More than $100 billion just for a few minutes of interruptions. Protection against, what is the industrial and commercial advantage of power quality? Protection against interruption of production. So if you have a good power quality, it is a kind of protection you are having. Otherwise, there will be lost time because for a few minutes there is no electricity. It may perhaps create problem in the industry like loss of production. Okay, like for example, there is a chemical industry, they are making some medicine or some other chemical product, and on the pipeline in the machine that product is flowing and suddenly there is no electricity. What will happen? We have to, chemical industry has to keep certain temperature and pressure, otherwise the product may not have the desired chemical requirement which are supposed to have for the drugs, for example. Then company has to clean all the pipes and the equipment, the product will be thrown away. So this is the loss of production. Efforts to restart, washing out everything from the pipe so that it does not go to new product and those things. Lost sales, now you will have the delay in deliveries and those things. Okay, and sometime if the power quality have like spikes and those things, it may damage the equipment, then the maintenance cost of replacement and cost of repair, those things. So that's why it is in the interest of everyone to have a good power quality to avoid those problems. For residential customer, no financial loss, because during the daytime, if there is no electricity 1 or 2 hours, it does not matter because nobody is at home. Kids are gone to school, adults are gone to work, so it does not matter. So there is no financial loss. However, when you return home in the evening, then you will see a blinking clock. You have to adjust those clocks, maybe 3, 4, 5 clocks you may have, so you have to adjust the time on everything. If the customer complains, the utility has to send a technician. But technician will come, what can he do? Okay, there was no electricity I remember 20 years ago, there was something happened and my VCR was burned out. Then I called Hydro-Quebec, oh, there was not good power quality, my equipment is damaged. So technician came, that's fine, the technician came, but he did nothing happened. So, but anyway, the utility company has to send someone, so it costs money, right? Bad publicity of the utility, Consumer Protection Group may ask for the inquiry of poor power quality. And in that case, utility will have to hire an advocate. So that costs. So bad publicity is not good for the utility company. Categories and characteristics of power system electromagnetic disturbances. First, the impulsive transient, you can see. So in certain, you see microseconds, you have 20 kiloampere of current for few microseconds. So this is impulsive transients. Okay, positive or negative unidirectional, very rapid increase in voltage at high frequency, independent of source voltage frequency. Suppose you have 50 Hz or 60 Hz, but it has nothing to do with this. It is in microsecond high frequency. Impulsive over voltage is characterized by rise time. So you see, this is an example, impulsive voltage. So rise time is this, 1.2 microsecond. Peak value, for example, it is just an example, okay, 2000 volt in 1.2 microsecond. And drop time to 50% off. 50% means 1000 volt. So here you can say this is the drop time up to the 50% of peak value, maybe 50 microsecond or something, that depends. Impulsive over voltage is diminished rapidly depending on the increase in the distance between the perturbation source and the load. Impulsive over voltage is caused by lightning stroke, network manipulations. Oscillatory transients, this is just an example of transient caused by capacitor switching, back-to-back capacitor switching. So you can see oscillatory transients are there, high frequency oscillatory transients. Instantaneous value change rapidly independent of the source frequency. So oscillatory over voltage is characterized by spectral content, its duration, its amplitude. It is frequently encountered in distribution network, caused by mainly by the capacitor banking. It may be depending on the capacitor and inductance, it may be high frequency, 50 kilohertz or 500 kilohertz or 5 to 500 kilohertz or less than 5 kilohertz. Transient phenomena may cause the following problem: equipment damage after the lightning stroke, breakdown of distribution transformer after thunderstorm, breakdown of customer's surge arrestor, tripping of variable speed drive without voltage sag or brief interruption, damage to customers' capacitors. Short duration voltage variation. Okay, so you can see for short duration, for few cycles, you have voltage sag. In Europe, they call it dip. So voltage sag may be between 0.1 pu to 0.9 pu. between half cycle and 1 minute. So that is short duration voltage sag. So if we say 20% sag, it means VRMS is 0.8 pu. Voltage sag is caused by high current flow due to system faults, starting of large motors, as we have already discussed. Short duration voltage sag may cause the following problems: abnormal variation of voltage, tripping of variable speed drive, tripping of arc lamps, temporary diminution of light. So here you can see one example, voltage sag caused by a single line to ground fault. So you can see voltage sag, it's around 20% of voltage from around 100 volt. It came to minimum 17.44 volt. So it is around 80% voltage sag for around 3 cycles. So this is just an example of voltage sag caused by single line to ground fault. And this is the voltage sag caused by motor starting. As I was telling you that if you have large induction motor, then for few seconds, like in this case 3.2 seconds, you have a voltage sag here. And 20% voltage sag because the voltage has gone up to 80% here. Short duration voltage variation, temporary over voltages. See, you have over voltages for short duration. Voltage swell, we call it swell. Sudden increase in voltage between 1.1 pu to 1.8 pu between half cycle and 1 minute. So swells are caused by unsymmetrical faults on the system, shedding of large load, energization of large capacitor bank. So these are the causes of the swell. Swells cause the following problem: abnormal variation of voltage, tripping of variable speed drives, breakdown of surge arrestor, temporary increase in illumination. So this is just an example of the swell. Okay, it is caused by single line to ground fault. Suppose there are two parallel lines, and if one parallel line is tripped, then the voltage may increase on the first line because there will be less current, less drop. So because of that, voltage swell is there. So in this case, you see maximum it has gone to 15%, around 15% temporary over voltage. Although this is not very clear, but it is here. Yeah. Short interruptions for certain period of time, there is no electricity. This is the short interruption. The voltage is between 0 pu and 0.1 pu. And there are three types: instantaneous, momentary, and temporary. Instantaneous if it is between half cycle and 30 cycles. Momentary if it is 30 cycles and 3 seconds. And temporary if it is more than 3 seconds and less than 1 minute. So this is short interruptions caused by open close cycle of circuit breaker of overhead transmission distribution line. It may cause the following problem: impact on industrial product, as we were discussing, tripping of motors, tripping of arc lamps. Under voltage, a brownout. So this is what I was telling you when we were young and I was in Bulandshahr, and many times voltage was there, but you could see the light coming out from the bulb was very less. And if you switch on the TV, then you can see the voltage is 180 volt or below that. So we used to have a regulator, voltage regulator. We used to move the switch so that the voltage, because it was perhaps stepping transformer. So this perhaps may be the strategy used by the utility companies to reduce the consumption, electricity consumption. If there is less energy is generated, they may reduce the consumption like this. So the voltage, maybe this is under voltage, 0.8 pu to 0.9 pu for more than 1 minute, caused by switching of large load on the network, switching off large capacitor bank. Over voltage, permanent, long duration voltage, permanent. If it is more than 1 minute, then we call it over this permanent, long term duration voltage variation. 1.1 pu to 1.2 pu, caused by switching off large load on the network, switching on large capacitor bank, like because you have switch on the large capacitor bank, so the capacitor bank is supplying the reactive capacitive current, so less current is coming from the source, so less voltage drop, so because of that there is a over voltage for certain time. Inadequate voltage regulation, incorrect choice of transformer tappings. Over voltage or under voltage are generally not the results of system faults, but the variation of load or network changes. Right? Some large load is put or large load is off or capacitor are on, off. So those are causing over voltage, under voltage. Voltage regulation equipment should be used to correct the problem. Sustained interruptions, if there are more than 1 minute, your voltage is 0 pu. This is called sustained interruptions caused by incident of permanent nature, like some storm came and the tree fell on the line or transformer burned out. Breakdown of power apparatus which requires repair to restore, like your transformer is burned out, now it has to be replaced or repaired. So sometime in Montreal we have hydrocubic truck is there, so that will come with a large transformer. Temporarily they will connect that transformer to replace this. This is what happens. Voltage unbalance. Three-phase system voltages are not equal in amplitude, or they are not shifted at 120 degrees relative to each other. So how you calculate the voltage unbalance in percentage? So this is the maximum of deviation between phase A voltage. See, deviation in phase A voltage, difference between the average voltage and VRMS, or phase B, DVB, or phase C. So you see which one is maximum, divided by the average voltage multiplied by 100, it will give you voltage unbalance in percentage. Usual causes of the voltage unbalance: single phase load of different customer on three-phase distribution network. Like sometime it happens in our ATS, also in my institute, that different floors, they are coming from different phases, so they may not have equal load, so that is the single phase load on three-phase system, different loads, so it may cause voltage unbalance, or it may cause by arc furnace or electric train, etc. Blown fuses in one phase of three-phase capacitor bank. So suppose you have three-phase capacitor bank, one of the phase fuse of the capacitor bank is burned out. So A is burned out, B and C they are still providing. So the A reactive current, capacitive current is not provided by the capacitor bank. So it will have more voltage drop, because the more reactive capacitive current is drawn for phase A from the source, while B and C they are still compensated by the thing. Geometrical asymmetry in overhead transmission lines. Why there will be a geometrical asymmetry in overhead? because sometimes transmission lines, they run for thousands of kilometers, like here also, but in Canada, we have in the north, we have thousands of kilometers away, we have Bay James, a big hydropower plant, and from there, 3,000-4,000 kilometers of transmission line is coming to Montreal area. But it is coming through the lakes, mountains, and other structures. So the capacitance between the overhead transmission line and the mountain, or the capacitance between the transmission line and the lake, the capacitor may be different, so it may causes the asymmetry in distribution. So how to correct it? So this is nothing new. This is the transposition of conductors we do. Like position A, phase A, after few kilometers, you change the position of phase A, and after again few kilometers, similarly phase B, after few kilometers, you physically change the position of the conductor like this. For the C, you can see. So this is called the transposition of conductor, which is normally used almost everywhere. For industrial customers fed by 120 kV or more, voltage unbalance in network is generally maintained at less than 1% or maximum 1.5% of voltage unbalance. In distribution network, it may be between 0.5 to 2%. Now the waveform distortion. There are 5 different types of waveform distortion. There may be DC offset, there may be harmonics, there may be interharmonics, notching, and noise. Those are the different 5 types of waveform distortion. Now if you see DC offset, it is the presence of DC voltage or current in AC network. DC offset is caused by the half wave rectification. You already know the half wave for single phase or 3 phase. So this may cause DC offset. Or there may be geomagnetic disturbance. So sometimes what happens on the surface of sun, there are some eruptions, big eruptions, thousands, millions of kilometers. It is big eruptions, and it generates high intensity electromagnetic waves. So sometimes you hear, okay, many satellites are out because of the eruption at sun. Okay, but now there are thousands of satellites, so other satellites, they take care of the communication system. But this happens very often. And even in Quebec, in my home province, in 1990 it happened. There was a big eruption of electromagnetic waves from the surface of sun, which reaches the earth between 24 hours to 72 hours. And that induces the current on the earth's surface on high transmission, high voltage transmission line. So it saturates the transformers and other equipment because this is a DC current which is induced. And this is what happened around 30 years ago, 35 years ago in Quebec. So all the high power networks were down for many days. So they did not know what happened, but then they analyzed it, then they came to know this was caused by those eruptions at the surface of the sun. DC component causes the following problems. May bias the transformer core so they saturate in normal operation. So basically you have to derate the transformer. So if the core is saturated, you cannot run the transformer at 100% load. You may have to derate it, otherwise it may heat up because of the additional losses and may reduce the transformer life. DC component causes even harmonics, second and fourth. It may cause problem in fifth harmonic passive filter. It may amplify fourth harmonic. Fifth harmonic filter may amplify fourth harmonic. Okay. It may cause electrolytic erosion of grounding electrodes and other connectors. Like the harmonics, you know, in US, in North America, we have 60 hertz, here you have 50 hertz, okay? So normally many loads are linear, but many different types of loads are non-linear in nature. Okay, so the current drawn is distorted. So if you do the Fourier transformation, you will come to know, we will see. See here, so if you have, suppose this current, okay, so if you do the Fourier transformation, the fundamental component of, this is the fundamental component, you can see, this, I think this is 50 hertz, and then you have the third harmonic, like in half load, in half cycle, you have 3 half cycle. Okay, so this is the third harmonic. Fifth harmonic, you have in 1 half cycle, you have 1, 2, 3, 4, 5. 5 half cycles for fifth harmonic. And for seventh, you will find the 7 half cycles. So frequency is 3 times of fundamental, or 5 times of fundamental, or 7 times of fundamental. So if you have just an example of a load, single phase diode bridge rectifier with RL load. Okay, so the currents, so here you have single phase like this. Okay, so if you see the currents here, this is the type of a square wave, and if you do the Fourier transform, you will see all types of harmonic, third, fifth, seventh, ninth, 11th harmonic. If you have single phase diode bridge rectifier with RC load, so you can see the current is very peaky and it has a lot of harmonics. In general, even harmonics are negligible. They are perhaps most of them present because of the DC component. For 50 Hz fundamental frequency, the principal harmonics present are third 150 Hz, fifth harmonic 250 Hz, seventh harmonics 350 Hz, ninth harmonic. See, and if you have a 60 Hz, then third harmonic 160 Hz, fifth harmonic 300 Hz. So this is how you can multiply 60 by 3, 60 by 5, and you can know the frequency of the harmonic. It may cause the following problem: increase in losses in conductors and equipment, fuses, transformer, wherever the current flows. Why the losses will increase? First thing is the ohmic losses, you know. And then perhaps you might have studied skin effect. Like skin effect is what? You have, suppose this is the conductor. If frequency increases, then the current will remain near the surface. Most of the current will remain near the surface of the conductor. So this is what is called skin effect. Because of that, the resistance increases, so losses will increase. But then you have electromagnetic losses also, like hysteresis losses or eddy current losses in core of the transformer or core of the machines. So hysteresis losses, they are proportional to the frequency, and eddy current losses, they are proportional to square of frequency. Okay, so suppose you have fifth harmonic, then hysteresis losses will increase 5 times in the core. But if you have eddy current losses, then 25 times more eddy current losses. So which will heat up the transformer, and you cannot load the transformer to the full capacity. You will have to derate the transformer, otherwise it will decrease the life of the transformer because of the extra losses. degradation and considerable reduction of capacitor's life, because capacitive reactance, 1 upon omega c. So if frequency increases, then Xc will decrease and it will attract the higher frequencies current. So more higher frequency current will be attracted by your capacitor. Like I was telling you example of the neighbor's load was overloading the capacitor of another customer which did not have the non-linear load, but non-linear currents, harmonic current generated by another customer, they were attracted to other capacitor nearby and it was overloading, heating the other customers, and it may decrease the life expectancy. Voltage distortion, it may alter the functioning of many devices, like because of the zero crossing and those things. Heating and torque pulsation in motors. Why there will be heating and torque pulsation in motors? Because of the harmonic. For example, I will draw a figure here. Suppose this is the stator and you are supplying the currents here, IA, IB, IC. Suppose this is an induction motor and then you have a rotor here, okay, conductors. So these currents, they will generate the rotating magnetic field in the air gap because of the fundamental frequency. Suppose we have 50 Hz or 60 Hz. So this is the rotating magnetic field which is generating a torque at the surface of the rotor, and rotor will start moving in this direction. Depending on the frequency, 50 Hz, here you have 50 Hz, this will be the rotating speed of the rotating magnetic field because of the fundamental components of the current. Now, suppose you have fifth harmonic here. You have fifth harmonic in B and fifth harmonic C. So, fifth harmonic current is there. Now, the fifth harmonic current will also generate rotating magnetic field, right? And that rotating magnetic field will rotate at what speed? 5 times of the speed of fundamental. Okay? So rotating magnetic field created by the fifth harmonic, and fifth harmonic is what? It's a negative sequence harmonic. It means it will rotate in the reverse direction. It will generate the magnetic field, rotating magnetic field in the reverse direction with 5 times of the speed, but 1/5 of the amplitude of the fundamental, right? So fifth harmonic will not go like this, it will go like this in the reverse. Suppose this is the direction of fundamental, F1 if we say, so this is the direction of F5 in the reverse direction, 1/5 of the amplitude, but 5 times the speed. So it will have its own torque at the surface of the rotor. So the vibrations will take place. Now suppose we have the seventh harmonic. Seventh harmonic in phase B and seventh harmonic in phase C. What is the sequence of seventh harmonic? It is the positive sequence. So seventh harmonic will generate the torque in this direction, but 1/7 of the amplitude of the fundamental, but 7 times the speed of the fundamental. See, the different torques are created at the surface of the rotor because of the fundamental frequency, because of the fifth harmonic, because of the seventh harmonic, maybe there are 11th or 13th harmonic. That depends what kind of voltage was there, right? So this will cause heating and torque. This is what is the torque pulsation. And heating, why heating? Because you have a fifth harmonic, you have a seventh harmonic. So in the core of the machine, there will be ferromagnetic losses, hysteresis losses, eddy current losses. Hysteresis losses will be 5 times, or eddy current losses will be 25 times. So this will all cause the heating of the core of the machine. Telephonic interference is caused by the harmonics. Please tell me when I have to stop for them, okay? But I will continue. Large neutral current consisting of third harmonic. So third harmonic is what? Zero sequence harmonic. So this is what? There are 3 currents coming, ABC, IA, IB and IC. So in ideal condition, the sum of 3 currents should be 0. But if you have the harmonics, third harmonic is zero sequence harmonic, IA 0, IB 0, IC 0, they are in the same phase. They will not cancel out. The sum of zero sequence harmonic is not 0, it is the sum. Basically, it will increase. So this is what happens, that if you have a non-linear load, different harmonics are generated, including the zero sequence harmonic, third, sixth, ninth, but not sixth, sixth is an even harmonic, maybe the 9th and 15th and so, and they will add up and finally it will go to the neutral. And that neutral current may be 2 times, 3 times of the rated current of the cable, neutral cable which you have put. So that may become heated. And if the engineer does not pay attention, it may also burn out. So sometimes, in the worst case, it may happen. There are so many problems caused by harmonics. Many other problems. Malfunctioning of energy meters and protection relays and circuit. This is just one example. There are many standards for harmonic producing apparatus connected on electric motor. 2 important standards, IEEE standard 519, which was originally introduced in 1992 and it was very popular standard, and that standard is still going on. What they have done some minor adjustment in 2014, and then 2022 also they did minor. But most of the things still remain, the harmonic limits and those things, they still remain the same. So what is the title? IEEE standard, initially it was IEEE standard recommended practices and requirements for harmonic control in electric power system. But later on in the modification they dropped this term. So now I see IEEE standard for harmonic control in electric power system. This document provides guidelines for harmonic current and voltage distortion levels on distribution and transmission network. And there was a second standard, IEC 555-2, but it has been superseded by 61,000 this. So this is to set the harmonic emission limits for appliances and similar equipment connected to public low voltage power network, but this is especially European countries, they follow it. But in North America, we follow IEEE standards. Then another way for distortion may be interharmonics. So what is interharmonic? See, this is, suppose we see, okay, this is the current, it is distorted and it has, see, 1, 2, 3, 4, 5, 6 and half, 6.5 half cycles. It is not five cycle, it is not 7 cycle, 6.5. Okay, so this voltage and current having frequency component that are not integer multiples of the source frequency are called interharmonics. So these are interharmonics. These are caused by non-linear loads, for example, arc furnace, static converters, cycloconverters. Sometimes utilities inject telecommand signals of interharmonic frequencies to control consumer relays. So this is what done by some utilities companies. Interharmonics cause the following problem. Same type of problem as caused by abnormal harmonics. Overloading of series passive filters. So because it may not be 5, it will be 5.5 or 4.5, but it will overload your passive filter. Drop of voltage during commutation, notching. So earlier I was thinking they are still talking about notching. This was in 1992. But then I verified in IEEE Standard 519 2014 and even 2022 they are still keeping this thing because thyristors are still very much in use for higher power application. Okay, so this is what is the notching caused by commutation overlap. Commutation overlap, suppose I draw a diagram. You already know, perhaps many of you already know commutation overlap. So this is by one set of, suppose we say it is a single phase load, one set of thyristor IT1, IT3, then these currents are by IT2 and IT4. So this is the ideal condition that you are considering, that they are switched on and off instantaneously. But in actual practice, it does not happen like this. You see, there is a commutation overlap. Okay, so during that time, both sets of thyristor, they are in conduction. Okay, so this is the commutation overlap and it causes the voltage drop. During the normal functioning of converters, AC source inductance prevents the instantaneous current, because in ideal condition we say, okay, we are not considering any inductance or impedance, so we could see the straight line increase or drop of the currents, but in actual practice that inductance prevents the instantaneous change of currents. So because of that there is a overlap. This overlapping phenomena causes the reduction of voltage called notching. So you can see this is the depth of the notch and this is the width of the notch at say some alpha degree when we switch on the thyristor. Depth of the notch, you see this is the load, this is the source, and this is the principal transformer, this is the reactance of the principal transformer, this is the reactance of the cable, and this is the reactance of isolation transformer. And if you see this point of observation from here, so you can see the depth of notch is equal to the reactance of the principal transformer plus the reactance of the cable plus isolation transformer. So if you have very less value of reactance of principal transformer, then you can reduce the depth of the notch. And width of the notch is given by this formula, and if you calculate the surface, so this is the depth multiplied by the width given by this equation. The limit generally admissible for the depth and surface of the notch is defined in IEEE 519 standard for 600 volt distribution network. So depth, and this is the surface, sorry, this is written in French, special applications, general systems and dedicated systems. So limits are different. Like you have a special application, like you are in the hospital or an airport. So limits are very severe. You cannot have more than 10% depth. And this is the surface, voltage microsecond. For general system, it may be increased to 20%, and for dedicated system, you may even go for 50%, because there is no other client, customer nearby, so it will not affect the other people, so that's why they allow those limits. The main problem caused by notches is about zero crossing synchronization of converters with source voltage, because notching may cause false zero crossing. For example, here we saw this depth, suppose it goes like this, then it may be seen as the false zero crossing, and your converter may try to synchronize with this. Mitigation methods: adding an isolation transformer or a line reactance for each drive, which will increase the value of XTI, will reduce the depth and surface of the notch. Adding a filter at the source of the drive, this filter may solve the problem. Okay. Noise, as you can see, these are the undesirable signals. So we are still talking about waveform distortion, because we saw that there are so many causes. These are the undesirable signals with minimum band width of 200 kilohertz superimposed on voltage or phase current, or even on the neutral current. Noise is caused by power electronic devices, arc equipment, uninterrupted power supply, improper grounding. Noise causes the following problems: malfunction of electronic devices like microcomputers and programmable logic controller. Mitigation solutions: you may use filter, isolation transformer, line conditioner. Now coming to the flicker, voltage fluctuation, you can see the voltage fluctuations like this, and this is the amplitude, plus minus maybe 2% or so. So this is called the voltage fluctuation or flicker. Flicker causes physical discomfort to the eyes because of repetitive change in the illumination of the light. Most of the apparatus remain unaffected by this phenomena. Flicker is caused by low frequency, 5 Hz to 15 Hz, low amplitude variation, plus minus 2% of the voltage. Rapid change in industrial load, for example, soldering machine, rolling mill drive, arc furnace, large motors with variable load may cause the voltage fluctuation. So earlier we were thinking that, okay, voltage fluctuation, flicker is there, and it causes the incandescent lamp to blink like this. But finally, I found out that it affects LEDs also. Because once I brought LED lamp and I put in my house and I used a dimmer, and at certain value I saw the LED lamps, they are also fluctuating. Okay. Even voltage fluctuation instability can cause LED lights to flicker. LEDs are sensitive to voltage changes, and when the voltage supply to them fluctuate, it can disrupt their steady illumination and result in visible flickering. LED light flicker may be caused by voltage fluctuation incompatible dimmer switch. So in my case, because in Canada we don't have voltage fluctuations, but then I realized because the dimmer I bought from somewhere else and the lamp bulb I bought somewhere else, perhaps they were not compatible at certain limit. So incompatible dimmer switch may cause it. Overloading of the circuit, too many LODs are connected to a single circuit, poorly matched power supplies and voltage instability, this may cause. Maximum sensitivity of the eye and its tolerance to flicker is between 5 and 15 Hz. So, yeah, it's already, how much time have taken? Oh, okay. Okay. Yeah, okay, sure. Yeah, sure. Okay. So I can leave it live.